Good evening, young people. We're going to do Sig Figs Part 2 right now. We're just going to do it back to back. I'm taking my glasses off so there's no glare on me. So here we go. So calculating with Sig Figs practice. We just talked about calculations at the end of the last video and what we do. We know when we add or subtract, we have to think about significant place. And we have to go with the least significant place that all of them have significance in. When we multiply and divide, we're talking about number of significant figures. So the one with the least number of significant figures is what we use to figure that out. So here we go. The first problem is 15.30 grams divided by 6.4 milliliters. Well, we put that in our calculator, we get this number, 2.390625 grams per milliliter. But that's not the right answer. The right answer has the right number of significant figures. So let's look at the significant figures. So 5.30, well, there's a zero, a trailing zero, but there's a decimal point. So that means we have 4 significant figures. 6.4, well, that's easy, 2 significant figures. So that means our answer has to have how many significant figures? Yeah, only 2. So that means that we are going to cut that off right there. So does the 9 make the 3 round up or round down? Does it stay the same? And the 9 makes the 3 round up. So our actual answer is going to be in 2 significant figures, and that's going to be 2.4 grams per milliliter. Okay? Addition and subtraction problem. Remember, we have to talk about significant place, and we can do this. 18.9 minus 0.84 grams, and we get 18.06 grams. But we have to look at place. So when we look at place, we see the last significant place is the 10th place. So we stop right there. We have to stop it right there. The 6, though, we have to look at the 6 because we have to see if it's going to round the 0 up. Because it's a 6, it does round the 0 up, so we get 18.1 grams. So as you can see, multiplication and division is much less complicated. We're just counting sig figs, the least number of sig figs, and that's the number we approach. Addition and subtraction, a little bit more complicated, and we have to think about significant place, okay? So scientific notation, powers of 10 in scientific notation. Basically, we talked a little bit about this. Powers of 10 are like moving a single decimal place. That's all it really is. Excuse me, I need to take a drink. So powers of 10, so if I go 1 power of 10 to the right, I go 1 place to the right. If I go 1 power of 10 to the left, I go 1 decimal place to the left. So that's what we're talking about by powers of 10. So rules for writing numbers in scientific notation, pretty simple. We only write the significant figures. We don't write anything that's not significant. So any trailing zeros without decimals we don't write. Any leading zeros we don't write that are not sandwiched. Only significant figures get written. We place the decimal point after the first digit because we want to make a number that has a value between 1 and it says 10, but we don't want 10. We want 9.99. So basically something that is greater than 1 and less than 10. So greater than or equal to 1 and less than 10 is the number that we want to get in scientific notation. That's what we end up with. Then we're going to use the correct power of 10 to place the decimal properly as indicated. So here we go. Positive exponents push the decimal to the right. The number becomes larger and is multiplied by a power of 10. Negative exponents push the decimal to the left and the number becomes smaller and is divided by a power of 10. So 10 to the 0 is 1. So some examples. 3,400 insignificant figures. That is not the right answer. That should be a 4 right there. Sorry, that should be a 4, not a 2. Sorry about that. So, but what we do is we want to place the decimal point right there to make the number that is greater than 1, greater than or equal to 1 or less than 10. To do that, we have to move the decimal point 1, 2, 3 spaces to the left. That's 3 positive spaces. So we get 3.4 times 10 to the third. Here we have a number 0.0120. So what do we do there? Well, we want a number between that is greater than or equal to 1 and less than 10. So where are we going to put our decimal point? We're going to put it right there between the 1 and the 2. That means we need to move our decimal point 2 places to the right. Well, that's the negative direction. So it's 1.20. Why is the 0 included? Because this 0 is significant. It's a trailing 0 with a decimal point. So 1.20 times 10 to the negative second. So if we have 65,000 kilograms, what do we have? 6.5 times 10 to the 4th kilograms. Why? Because we put a decimal point between the 5 and the 6 right there. That's where our decimal point's going to go. That means we need to go 1, 2, 3, 4 places to the left. That's positive. So we have 6.5 times 10 to the 4th kilograms. So converting into scientific notation is pretty simple. Converting back, all we're doing is counting again. So we're just counting back and forth here, guys. That's all we're doing. So large numbers are positive exponents, small numbers are negative exponents. We only include significant figures, so that's the basics. Scientific notation practice, let's try. So we have 2,400,000 micrograms. What are we going to do? Well, remember, we need our number that is greater than or equal to 1, but less than 10. So our decimal point is going to go right there. What does that mean? We go 1, 2, 3, 4, 5, 6 places to the left. That's positive. So we're going to end up with 2.4, times 10 to the 6. Why don't we include any of those zeros? They're not significant. There is no decimal and they're trailing zeros, so we're good. 8, okay, here we go again. We need a number that is greater than or equal to 1, but less than 10. So where are we going to put our decimal point? We're going to put it right here between the 2 and the 5. So now we have to move our decimal. We go 1, 2, 3 places, but remember we're going right. That's the negative direction. So it's going to be 2.5, we have to include the 6 too, 2.56 times 10 to the negative 3rd kilograms. 9, 7 times 10 to the 5th kilometers. If we go backwards, I'm sorry, this is going to go backwards. We have scientific notation, now I want to go backwards. Well, what do? Well, I know that I went to the right with my decimal, so to figure it out, I'm going to have to go the other way. So my decimal point is right there. I'm going to go 1, 2, 3, 4, 5. My decimal point is going to go right there, and I'm going to fill zeros. 1, 2, 3, 4 zeros. So 0.00007 kilometers. Okay, number 10, same thing except we're going backwards. We're not going into scientific notation, we're coming out of scientific notation. So times 10 to the 4th tells me that I moved left to get that, so I've got to move right to get it out. So here we go. I go 1, 2, 3, 4 places. I put zeros in the places that are empty to place hold, and so I get 62,000 millimeters, okay? It's pretty simple. It basically, a times 10 means that I'm moving a decimal place. That's all it means. So if I'm going to the left, I'm multiplying by 10. If I'm going to the right, I'm dividing by 10. When I switch back from scientific notation into regular notation, I do the opposite. So if it was negative and I went right to get the negative, I go left to go back. If it's positive, I went left to go positive, so I go right to go back. So I'm just using the backwards kind of thing. Calculating with scientific notation. This is really easy, and on your calculator it can be really simple. So I'm going to skip through this pretty quickly. But on your calculator, I want to make sure that you know how to kind of do this a bit. You're going to be looking for a couple of keys on your calculator. If you have a graphing calculator, you're going to see an EE key on your calculator, but it's a second function key. So you're going to have to press second function and the EE key if you have a graphing calculator. And that EE key is located as a second function key above the number 7. So it is above the number 7, and I believe that the key that it is, a second function of, it looks kind of like a comma, but it's above the number 7. You will have to press the second function key. If you do not have a graphing calculator, you're looking for a couple of different symbols. You're looking either for an EE symbol, an EXP symbol, or a times 10 to the n symbol. If you're not sure what your calculator does, bring it to me on Monday and I will help you figure that out, because you're going to need to be able to use that calculator. We are going to go over this again when we get to the part that we do this in, but I want to make sure that you know kind of how to do it. It's not hard. It's actually pretty simple. You can actually do it by hand if you really wanted to, but you don't have to. You can use a calculator. So what are you going to do? This is 3 sig figs. This is 2 sig figs. So we know our answer is going to have to be in 2 significant figures no matter what we do. So you're going to type on your calculator 5.44. Then you're going to find your EXP or EE key. If you have a graphing calculator, you have to press the second function to get to that. Some regular calculators have mimicked the graphing calculator, but usually you're looking for the EXP or EE key. Sometimes it's 10 to the n key. So you're going to press that, and then you're going to put in your exponent, in this case 7. Then you're going to put divided by on your calculator. Then you're going to put in 8.1. And again, we're going to find our EXP and EE key. Whichever one you have, it's one or the other, or the third one that we've talked about. Then you're going to put in your exponent, which is 4, and you're going to hit enter, and we get 671.6049383. Well, we know that that's not the right answer because we have to still do significant figures. So we have 3 and 2. So how many significant figures are we going to end up with? Yeah, 2. So we get 670 grams per mole. Now, because it was in scientific notation to begin with, we want it to be in scientific notation to end with. So again, where is it going to go? We have to have a number that is greater than or equal to 1 but less than 10. So the decimal point goes right there between the 6 and the 7. And we go 1, 2. So we're going to get 6.7 times 10 to the second. That gets rid of the 0 that is a placeholder. Notice that placeholder 0 is not there anymore. We don't need it because when we write it in scientific notation, all of that goes away. It's there. In other words, it's meant to be there. The 6 and the 7 are in the 100 and the tens place, but it's not. It doesn't have to be listed because it's in scientific notation. Okay? So average and range. Average and range are a way that we determine accuracy and precision. Average is a way that we show accuracy. Basically, we're trying to see how accurate our data was. Range is the way we show precision. So the smaller the range, the more precise your data was. The range is basically the difference between the smallest and the largest of your numbers. An average is exactly what you know an average to be. You add up all your numbers, you divide by the total number of numbers you had. So how can we tell if data is collected is precise and accurate? Average and range. So average, adding all of your data and dividing by the number of data pieces you have. And this gives you a number that's in the middle of your data. And it tells you what your data tells you about accuracy. Range is the difference between the smallest and the largest values measured. So let's look at an example. So using average and range, here we go. We have 4 thermometers. We see, okay, we can add all that up. We get 100.0. Why do I put the 0.0? Because those zeros are significant. I have significance all over there. The range, the highest was 100.1, the lowest was 99.9, so that's a range of 0.2. In the second thermometer, we do the average, and all I'm doing to get the average is adding them all together and dividing by 4 because there are 4 readings. The biggest one was 200.3, the smallest one was 97.5. We have a difference of 4.8. Okay, thermometer 3, our average is 98.5. We have 98.7 and 98.3. That's a difference of 0.4. Thermometer 4, our average is 97.0. The range is from 99.7 to 94.4. So the range is 5.3. Basically, this was the most precise reading. And it was also the most accurate reading because we're talking about the boiling point of water here. We see that we have another one that was pretty accurate. This one was pretty accurate, but it was not precise. This one was precise, but it was not accurate. And this one was neither. So this is both. This is just accurate. This is just precise, and this is neither. Okay? So you can see how that works when we use average and range to figure that out. Okay, percent error. Percent error is pretty simple. It indicates the accuracy of a measurement. So we're comparing it to a value. We have an experimental value and the actual or literature value. The experimental value is your value. The literature value is the accepted value, the one that is given to you. Either you look it up, I give it to you, something of that sort is going to happen. So here we go. We see that a student determines the density of a substance to be 1.40 grams per milliliter. Find the percent error if the accepted value of the density is 1.36 grams per milliliter. So we can see, here's our value, the value that we found. Here is the accepted value, and we put it here again because we're dividing it by it, and we multiply by 100, and we get an answer of 2.9% error. Anything that is less than 5% is considered really good. Okay, really good. And it really depends on the experiment, how closely you can get. So that's the end of that. Another 15 minutes has gone. Hopefully you'll get